Cool, so today we're going to talk about TEs, Trusted Execution Environments. It seems like there's a lot of experts in the room, so I don't know if I'm the most qualified to talk about that. If there's any insight or stuff that people are interested in talking about, then feel free to interject. But yeah, TEs, also called confidential computing, or these two concepts are kind of mixed up. Confidential computing. Let me write it up. So when I started getting into these things, I was kind of confused because there's so many lingo, there's so many terms and concepts and ways of doing things. And I guess you're going to see that pretty quickly. You know, like if cryptographers like Greek letters and one-letter variables, hardware people love acronyms. So that's something that's going to be a theme throughout this. This is our first acronym. This could be CC also, and you'll see a lot of that. So basically, the essence of these things is to be able to run a program without being able to see what's inside. And actually what people, I've seen that term being thrown, it's like protecting data in use. Because we know how to protect data at rest with encryption, and we know how to protect data in transit with TLS or these kind of things. But data in use on a computer, we don't really know how to do it, or at least before these technologies. There's been like some attempts in the past. I mean, you know, you've heard maybe of terms like secure enclaves, secure elements, HSMs, SIM cards, I guess, are secure elements. There's been a bunch of like different kind of hardware chips or stuff to try and achieve it. But today there's a lot of competition, and people have managed to bring these things in a very user-friendly package, let's say. Maybe we can try and talk about sort of what is out there as a developer if you wanted to touch these things. And maybe some people can help me because I never know what all the technologies are. But at least you have like Intel TDX, so that's the last stuff from Intel, which was kind of a, let's say it's an evolution from SGX, and I'll talk about the difference after. So yeah, just wait a bit. Yeah, Intel. And then we have AMD. The latest is SEV SNP. I know RISC-V has something. Actually, I'm not sure. I think they have something called Keystone, but that's still a research. Anybody wants to help me here? Actually, what's the latest? Nobody knows.
Yeah, no one's building it. Yeah, so lots of code open source from Keystone.
Right. So Keystone. Not sure if we can use it today, but
Keystone requires a hardware root of trust. So they separated the software and hardware.
Mm-hmm.
They have an abstraction, and you need an underlying hardware root of trust.
Well, I guess I'm talking about the more like hardware. So I don't know how the project worked. Maybe let's not get into the. Okay.
Whereas Intel and AMD are chips.
Right. Okay. So it's part of the solution.
Yeah.
ARM has.
Yeah, ARM has CCA.
Well, TrustZone and CCA. I'm actually not sure what the difference is between these two.
TrustZone is the older one, and the CCA is the newer one. I think they're
All right.
going to launch CCA pretty soon, and CCA is comparable with TDX. So that's going to be a virtual machine based.
Right. So I think SEV SNP as well. So we sort of have these three guys, and then we have like cloud people, and like so AWS has like Nitro enclaves. So let's write Nitro enclaves. AWS. What's interesting is that. So you know, again, like in cryptography, you're looking at different guys, and they will all use the same standard. Like they all use AES or something like that. But when you're in this world, everybody uses something different. Everybody does something different. It's very hard to, even though concepts translate from one side to the other, they all have their different acronyms and the different ways of doing things. And as we'll see, like my understanding of Nitro enclaves is that they trust much more the hypervisor, whereas these guys try not to trust the hypervisor. So you have different threat models. Even the threat models are not super clear depending on what you're using. And maybe one last thing I can say is that if you're using Azure or GCP, I believe you have the choice. I think on both platforms, you have the choice between TDX and SevSNP. I think that's what they do.
That's right.
Cool. Yeah, does that make sense for everyone?
You also mentioned GPUT.
Oh, the NVIDIA stuff? Or okay, so NVIDIA has something. That's a good point. NVIDIA, how is it called? GPU?
They call that NVIDIA confidential computing, but you can just say NVIDIA GPUT.
All right, NVIDIA thing, GPU, CC, or
Maybe, can I just ask
oh yeah.
something? So if you take a bigger step back, some people, at least academics, they present this trusted execution environments in three broad families. The servers, which is mostly what you have on board now, mobile devices, and smart cards and secure elements.
Oh, right.
So in mobile devices and smart cards and secure elements, they have a bit more standards, it's called global platform.
Right. So here, I guess this is mostly like server and that's the focus, right?
It's a kind of broader context.
Maybe, yeah, I guess also like standards take time to happen. People need to agree on like what to standardize and cool. So maybe I can talk a bit about API. Oh, actually, maybe I should mention the fact that we sort of started with SGX or this kind of approach, or maybe. I'm not too sure about the history as well, but I feel like from maybe someone can correct me, but people started thinking we could verify a whole computer, and so they were like, okay, we're gonna do like secure boot or merger boot with TPMs, or like they were like different approaches and different ideas. And I think Intel TXT was that basically trying to do well, I mentioned TPMs. Maybe I'll write it down, but I'm not going to explain what these things are. Some of the ideas were like we're going to verify everything, and so we can trust what's happening after. And then they realized this was hard, and so SGX was like, okay, we're going to go to the other extreme, and we're going to only try and trust a very small enclave. But that was kind of hard to use. Like you had to work with a library, you had to write very low-level code. Developers didn't like that. Developers like to deploy, Docker images or these kind of things. And so this approach came out, so CVMs, confidential VMs, where you can just deploy an entire VM. Like you have an image and you can just deploy that. And I guess people are going even further. They're like, okay, developers really just like Docker containers. So we're going to do, I've seen that term before, confidential containers. Mm-hmm. And so, the what? Coco. Oh, is that what Coco stands for? Yeah. I thought Coco was confidential computing. Also, sometimes like acronyms will change over time, which is kind of annoying. But confidential containers are basically just give us a Docker file, we'll just deploy it inside one of these solutions. This is what Nitro Enclaves gives you, and I think Azure and GCP might allow you to do these kind of things. And of course, we have DStack that allows you to do these kind of things as well. Maybe I'll write this down because I looked at that recently, so people can be aware of that.
If you write down DStack, you should also write down Apocryph and Ruffle.
This sounds very hard to spell.
Well, Ruffle's ROFL.
Do you want me to write it down? What's are you spelling? Oh, okay. Rolling. Wait, is that an actual tool or is that a comment?
It's cool. It's similar to DStack, and it's a Web3-oriented one with
Okay. Is there another one you mentioned?
Apocryph, APOCRYPH.
Apocryph. They should change the name. Secret VM. Secret VM. All right. For the sake of completion. So basically, these guys are kind of hard to use because you have to boot your own image. So you have to figure out like, okay, what firmware to use, what OS to use, what file system to use, and of course you want to make sure that it's done in a secure way. So by default, when you launch a VM, you might trust a lot of things that the host is sending it. So Intel has like its own thing called TDVF. Maybe I'll mention it. acronyms, more acronyms. TD virtual firmware, and basically it's a thing to help you launch a secure image inside TDX. But at some point, if you're just a developer and you want to use these things, at some point, most likely you're only gonna care about Docker containers and you give your Docker compose file or something like that, and you don't have to think about that. Cool. I want to talk about the API. So, all right, we've talked about that. So API stuff. So confidential computing sort of gives you two properties. I mean, it's a way to see that. It gives you integrity over the computation vis-a-vis of someone else. And this is usually called remote attestation. But maybe this is also, maybe even as a server that wants to make sure that your VMs are well isolated and running the correct thing, this is also interesting without attestation. So maybe you can think of integrity as a separate property that's also interesting. And the other one is confidentiality. And this is basically something is computing, but we don't know what it is. There could be keys in there, there could be cryptographic operation, there could be encrypted data from the user, but we can't see what's happening there. Even if we have, and this is where it gets tricky, even if we have hardware or physical access to these things, we can't really see what's happening inside. And so the remote attestation part, you can sort of see that as a ZKP, and I guess confidentiality, you can see that as the ZK part of ZKPs. But it's a bit more than that, because ZK is confidential because someone else is running the thing and then giving it to you. So here I would even argue that it's sort of like FHE, when you're encrypting over, you're operating over encrypted data maybe, or even MPC, where data is coming from multiple places and you can do something over it, or maybe you produce a decrypted result, so it's functional encryption. So you sort of have this Saint Grail of a cryptographic black box that allows you to do anything you want in this sort of programmable space of cryptography. It's actually, like I said, it's easier to use because maybe it's Docker containers and you don't have to care too much about that. And it's also faster, it's way faster than MPC and these kind of things. So of course, this comes with a cost, and the security aspect of it is not like pure cryptography. You're not thinking, so that's the part where we talk about security. Or actually, before I talk about security, does that make sense for everyone? Okay, talking about security, like in cryptography, we usually talk about asymptotics, if parameters are large enough, we know that, if n is big enough, then the adversaries will have to do 2 to the n operations, and it's going to take a while, and it's unfathomable, and it's never going to happen. But in the hardware world, it's more of a the attacker has to spend a lot of time and a lot of money, and we think they're not going to reach that point. So the security posture is much different, and how we think about things is much different. Yeah.
I'm not sure, maybe, so I can put that as a question, but for this notion that you cannot see what's going on in the T, right?
Right.
Because the T lives in a host, right? And the host is considered to be untrusted. So
right.
when you load the program in the T,
so usually you have a host.
So I think maybe more accurate to think of it that you know which binary is running in the T because it has to go through the host.
Right.
Loaded into the memory, encrypted memory. But the inputs you provide to the T are the ones that you can have confidentiality guarantees over. Because you can send inputs encrypted to the T that are going to be decrypted within.
Right. But I feel like that's still a distinction because your input could be a program to run, for example.
Sure. But that program has to be received by an enclave binary. And that enclave binary, I think it's really hard to assume that it's going to be not known. At least it's binary. Do you understand? Because this also becomes important in the context of remote attestation. In order for remote attestation to make sense, at least it doesn't have to be this way, but what the remote attestation is going to tell you is that the hash of the binary that is running within the T. And I think you can maybe make parallels with.
I think it's the same with zk though, because you have a verifier key, which is like a description of, even like an obfuscated description, you can think of it, but it's. I would say it's similar, or you can achieve similar things, or or at least from a developer perspective, I think you can. This way of seeing it as a black box that provides these things, I think is useful enough. Or
I would ask later also, but like, how would you run an encrypted program, or like, none of those 4 crypto analogies you gave really like let you run an encrypted program, like obfuscation you mentioned, like that kind of is.
Wait, how you would run an encrypted program? Like you would just have your T would implement a VM, like, and you would just send an encrypted program that the T would decrypt and then run, right? Is that what you were asking?
Yeah.
Like the Grammines of the world, or?
Well, Grammene doesn't bring that in, but I think Grammene encrypts your program.
Wait, what is gramming?
It was like the framework on SGX that almost was as good as running confidential.
Oh, okay. All right. Cool. All right. Yeah, we'll talk more about like what exactly can the host actually see what's in the T, like what's going on there. But security-wise, I should mention that since SGX came, I don't know what year it came out, but there has been a lot of attacks. Like academics have been looking at it, and have been like attacking it, mostly from software side channel perspectives. So a lot of side channel. I don't know how to say that word. Side channel. A lot of side channel attacks. A lot of them are hardware attacks, but there's been like, I think plunder vaults where like you're in the host and you lower the voltage of the CPU, and the CPU starts making fault, and there's ways to attack things like that. And there's also been attacks that extracted the keys from SGX. So like some attacks have been pretty bad, and it's important to mention. So it's sort of it doesn't mean that these things are unusable, but you sort of have to. You cannot see them as perfect cryptographic primitives, and you have to understand the security in the applications that you can implement with them are somewhat different. What else did I want to mention? Oh yeah, and I wanted to mention hardware attacks. So I haven't seen too many. Like it's very rare to see hardware attacks on these kind of things. I don't know why. Maybe my explanation is that it's just very expensive to attack these things. Like CPUs are very small. I'll talk about the root of trust, but I mean, spoiler alert, my way of thinking about it is that as long as the CPU package is secure and by the way, I'll talk about that also. As long as the CPU package is secured and you're sort of fine, and that CPU package is very small, it's like alien technology for a lot of people, unless you're Intel. And I've heard that even Intel doesn't understand how they produce these things anymore, because they have a machine that produces another machine that produces, at the end, some CPU. So it sounds like hardware attacks are very hard. And the what? That's not my, yeah. I'm not a hardware person.
Sure. So maybe if it's useful for this crowd to give a slightly different perspective. From talking to hardware researchers, especially people in Belgium, KU Leuven,
NXP or
who hack hardware all the time. That's why I mentioned earlier these 3 broad categories of smart cards, secure elements, mobile devices, and servers. They don't want even to spend time on trying to attack Intel, SGX, and the likes, because these are not considered to be secure against hardware physical attacks. Okay, so if you talk about physical security,
right.
Intel itself and the likes don't claim to be secure against physical attacks. So now, going back to your question, why we don't see such attacks? From my understanding, to talk to them, they don't even want to spend time on that. They want to get a paper.
Chess doesn't accept
people
that.
will not be able to say, you're not proving anything. Intel itself says it's not secure against physical attacks, so it's not worth the time, especially reverse engineering.
So I think it's still a spectrum. Like it sounds like some. I mean, sure. Like if you. So that's interesting, right? Like you're giving hardware in the hands of like the threat model is like it's in the hands of like potentially malicious people. In this T case, it's like the hosts or the cloud providers are malicious. And so if you read the paperwork, it sounds like they're defending against some hardware attacks, but it's not clear exactly what the defenses are, exactly how they defend against different attacks. I mean, I'm imagining hardware security is basically you're looking through a list of attacks and you're trying to prevent all of these attacks. Can people point lasers at it? Can people like throw acid at the chip and like see what's inside? Can someone man in the middle this chip and this other chip? And you're just going through this list and you're like, okay, there's crazy attacks, right? You can also like look at the memory and you can freeze the memory. It's called cold boot attack, so that you can unplug the memory and the data doesn't disappear and then you can plug it somewhere else. There's so many things you can do. Apparently, some of these attacks are taken into account in the threat model. But that goes back to what I was saying. The threat model is not super clear. For sure, some other type of like secure elements and kind of things, these kind of things are much more secure.
Just to give you a different, I was in Belgium 2 weeks ago and Kirillov, and I visited their lab, their hardware lab. And
Right.
the guy told me for SGX, they have the other building where computer science people, they attack it. They don't need to do attacks with the hardware, on the hardware level. For them, it's the doors are wide open for them. It's not
Okay.
so bad, right?
Oh yeah, no, that's an interesting point of view. Yeah.
And there's a good paper called Intel SGX Explained,
Right.
2016, but in my opinion, it's one of the best papers to understand SGX itself. But it applies to TDX too, because TDX uses the same kind of hardware primitives.
Right.
It clearly says that power analysis attacks, electromagnetic radiation attacks, and fault injection attacks, Intel does not protect against that. Chip attacks. So anyways, there's no claim on the part of the...
I mean, they do say that side channel attack. I mean, I don't know what's the latest today also.
I still don't think they've gotten a full root of trust out of any generation of SGX though. Like there was the guy last August who I think got relatively close. It was like one step away. It was on one specific unit. Exactly, yeah.
But I mean, this point is like an uncanny valley. It's like, why don't we see more of those? Well, like he's totally right. Like the security researchers in academia who could do this don't get enough points for even succeeding at it. That it's not.
This is an interesting.
Yeah, then it's like too expensive for startups to casually do it, and that's a. Yeah.
So I mean, it's hard to estimate also like how much money it costs, because that's also a cost, I guess, if you're doing hardware attacks.
For the power analysis attacks, not to take too much time on this, but
Yeah.
an oscilloscope, I don't think it's that expensive. Let's say 20 to 50K, I don't know. And I was told by some hardware researchers like maybe a weekend. A grad student. So it's just a question if people would decide to put a bug bounty, maybe we would see people doing it for just money, like grad students.
Okay. Right. So okay. Interesting. Interesting perspective. Security is debatable. There's different type of applications. I'm not taking sides. I'm here to give an overview. Obviously, people think this is very interesting, and maybe I can talk about more why this is interesting and why people think the security is acceptable. I think the last time I explained that to someone, I was talking about perfect security, as in like cryptography is perfect security, and all the T's are sort of bringing acceptable security for a lot of protocols. And so, for example, and I'm going to talk about obscurity also. You made me think about that word, so I jotted it down. But security through obscurity is a big no-no in cryptography. But when we look at these things, it's actually an advantage, because the more obscure these things are, the harder it is to attack them. And we've seen that with nitro enclaves. Like there's basically not that much research because nobody has access to these things. And so as an attacker, if you have to attack it, it's not only very expensive, you need insiders inside of AWS, you need, the bar is much higher. And so now you're thinking, okay, like I'm not talking about like, well, for some kind of applications, then this is a step up from just running a VM in a cloud. Now you can run a VM that runs in these TEs, and it's non-debatable that you get some security improvement from it. You don't know, but it's hard to tell what's the actual monetary, or, I mean, you gave us, someone say it takes a weekend and 20K or something like that, but it's still hard to
just link to this obscurity through security. One of the feedback I get from hardware researchers, they don't see they don't, because you have to do, most of the work will be reverse engineering. And then there's a risk because after spending months reverse engineering the thing, are you going to find what you're looking for? So a lot of people don't want to take that risk of spending months reverse engineering the chip because it's not open source.
Yeah. Or either you don't have access to it, maybe the incentives are not right. Okay, so let's move on. Let's move on from security, but yeah, good points. So I mentioned that I think the security comes mostly from the package being small, debatable, but this is sort of what Intel TDX and I assume others will tell you. The root of trust, or part of the root of trust, is the CPU package. Of course, there's like a key from Intel that's fused inside of there, and so you're also trusting that there's a PKI, a public key infrastructure, and there's some root Intel keys that you also have to trust if you're using the remote attestation part. Actually, even if you're not using the remote attestation part, some of the software to make it work is actually signed by Intel, so you have to trust it everywhere. This idea of like, okay, let's think about what we're trusting in this landscape is called the idea of TCB. If you've ever designed something that was a bit complex and you really wanted to try to make it secure, you've for sure came across that word. If you don't know, it's called trusted computing base. And basically in TDX, well, I guess I'm going to focus on TDX mostly because that's what I was reading, but hopefully this concept translates. And in TDX, it's basically I'm not going to write TE here, I'm going to write the CPU or the CPU package. This is part of the TCB, so you're trusting that the microcode, the circuits, all the components on there, and I'll talk more about the components, are trusted because they're part of the same package and it's very hard to attack. And also the software that you will load is also part of the TCB. And maybe this is interesting to mention, but the approach of TDX is that you have this TDX module. TDX module. And so they often say that they don't trust the VMM or the hypervisor or VM manager, the software or hardware that's in charge of launching VMs, exiting VMs, etc. They usually say that they don't trust that, but I mean, their TDX module software is basically a micro hypervisor that the hypervisor makes use of. And so you're also trusting that this software is correct and these kind of things. So the way Intel TDX works is basically they ship with this package that basically has TXT. I mentioned it here. Maybe I'll use different color. So they use TXT, not the entire thing, but there's something in TXT called SEM, more acronyms, authenticated code. And this allows you to load software in a secure way. And the software has to be signed by Intel and these kind of things. They only use that to load the TDX module. Technically, there's some other stuff in between, but it doesn't matter. And that's the only software they really load, which is that's micro hypervisor. They also rely on SGX. So actually, they didn't get rid of SGX. Inside the CPU, you have an enclave. They call it the quoting enclave because it creates these, these attestations or quotes. And they reuse SGX for that because they already had the machinery for these kind of things. And they also make use of VMX. VMX was the extension set to just manage VMs of Intel, and they basically extend that with a new mode. It doesn't really matter to understand these things, but it's called the SIM mode. And that basically allows you to launch secure VMs instead of normal VMs. So these are what they call confidential VMs. Confidential VMs, or if you want more acronyms, they also call them TDs, trusted domains. Trusted domains. And finally, they also use another thing. It's called multi-key total memory encryption. So here you have it. I think these are the main components. And this is the thing that allows you to encrypt the memory. So remember, we want to protect data in use. There's going to be the state of the software and the state of the CPU, the image you're running, all these things. You want to encrypt all of that, and you're going to use this multi-key because you want different confidential VMs to use different keys. Yeah, does that make sense? We have a CPU package. We build on top of VMX for VMs that we extend. We have some MKTME for encryption. We have TXT with ACM to just load that micro hypervisor. And we have SGX to, at some point, we're going to want to sign stuff with some key that's signed by Intel so that people can verify it.
Can you say the quoting enclave, what does it sign in this context?
So it's kind of weird, but basically the quoting, there's a mechanism in TDX where different TDs or CVM, you're running different TDs, they can communicate between them, and they can also communicate between them and the QE, so the SGX, via like a MAC, HMAC. And the application basically is in charge of they'll say, okay, these I think it's 64 bytes, 64 bytes of arbitrary data that you want to sign, and a bunch of measurements, but I haven't talked about the measurements so far. And they send that to SGX. SGX understands that it comes from an actual enclave on the same platform, and it signs that. By the way, sending, I think, goes through the host. So they send that to the host and then back to the QE, and back and forth. And yeah, you get some sort of a report that has a bunch of stuff in it, arbitrary data that's signed for the application, and some measurements. And I'll talk more about that. Yeah, does that make sense? Any comments? All right. So what can I talk about? So there's something interesting that I can mention before I talk about measurements, which is this idea of actually I should also talk about firmware. Maybe I can mention it a bit more. So there's this idea of when you encrypt memory that you don't want. So this is memory of that the program is using. If you turn off the computer or the TD, then this memory is going to go away, right? So you also have persistent data, and you sort of have to figure out for yourself how to deal with that persistent data. So most of the time you just encrypt it. The problem is that TDX doesn't prevent rollback attacks, so maybe that's interesting to mention. So here's your hard drive. So your application will eventually put some data here, it's encrypted and everything, but if the host takes a snapshot of that data at some point, and then you update that data, they can roll it back. They can just set that data to the previous data. It's encrypted, they don't know what it is, but it's a previous version. And so TDX sort of has to deal with that, or SGX and all these solutions. Usually so from what I've read, the two major solutions against rollback. Does that make sense, this attack, rollback attack?
Yep.
So you really want to prevent the host from changing the memory, or a hardware attack from changing the memory to a previously encrypted version of the memory. And so here, either you use these hardware time counters, and from what I've read, they're very expensive to use. They have limited usage. You can't use them after a certain number of times. They're very slow, so they're not a great solution for a lot of applications. So either I don't know, hardware counters. Let's call that. Or basically you have a committee of enclave running different places, and you just run a consensus protocol in between them, and they will agree on what's the latest state. So that any consensus in a blockchain, you cannot revert back. Yeah, makes sense?
Could you checkpoint on a chain? Let's say a public bulletin board, you put your last index.
Oh. You could checkpoint on a chain and say this is the latest point, the latest agreed. I guess you could do that, but I mean you're relying on consensus, right? Eventually,
Sure.
of the chain. Yeah.
It's the same as SPF, roughly.
Yeah. I mean that's a good question. But yeah, but then you trust. Yeah, I guess you trust the chain instead of talking to these guys directly, and maybe there's no way to recover if you're diverging, or like a BFT. Also, you're supposed to be able to recover if you don't see the same state as others. So maybe there's some. But yeah, I mean, oops. Yeah, not too important, I guess, but that could be a solution. Another thing that's important, or maybe interesting to mention, is that where is the RAM? There's some RAM. Like this is the RAM, I guess. You have some dynamic memory somewhere, and at some point you're gonna put the image you want to boot, and then you're gonna want to sort of lock it so that TDX goes into this mode where it's bringing these instructions of that program inside the CPU, and then it can run it. And remember, we trust the CPU, so that's really the root of trust. As long as we can bring these things in the CPU, we trust that the CPU will correctly execute these things, the instructions will be correct, etc. The problem is that obviously this is too big to bring in the CPU. The CPU has some memory, right? There's like L1, L2, L3 cache, but this is limited. Like you're limited to like 64 bytes, I think, for these cache lines. And so what they do is that basically they have this thing where they will, and I guess this is where I can talk about measurements, which is interesting. They will bring this thing line by line in the CPU, or at least that's my understanding. And when they're in the CPU, they will encrypt these and put it in the memory of the confidential VM, using, by the way, this thing we've seen here, the total memory encryption. They will assign a key to encrypt that, and they will measure this thing at the same time. So they're doing this kind of atomic operation to prevent any sort of race condition attacks where you measure this thing, and I explain what measurement means. You measure this thing, you're like, okay, we locked on this thing, we're gonna execute this thing, and then someone modifies that memory. So they're trying to prevent against these kind of attacks. And okay, so what are measurements? Measurements is basically, I think it came from TPMs. I don't know if people were doing that before TPMs, but it's the idea that instead of enforcing what's gonna get booted, we're just gonna allow it to be dynamic. We're just gonna allow like random things to be booted, but we're gonna measure it. And we're gonna make sure that these measurements cannot be faked, and we cannot reset these measurements. So I think originally it started as a separate discrete chip where you had like some registers. I think they were called PCRs, but it doesn't really matter. And the first thing to boot, bootloader 0, will basically hash whatever it's booting and put it in one register. And the next bootloader would hash whatever it's loading and would put it in the next register. And if you wanted to reset something, you couldn't. Like you had to turn off the computer and restart it. And if you wanted to, you could also extend these things. I don't know if it matters for my explanation, but you can imagine that extending something doesn't remove a previous value. So, I mean, we're here to talk about cryptography also, so I guess extending is basically like if you're hashing BL1, you're measuring BL1, you're hashing it, and I imagine you wanted to measure BL2 in the same register, you would just chain the hash. But the idea here is that you can't reset these to 0 unless you're turning everything and you're restarting from scratch from the first bootloader. And if you trust the bootloader 0 to do this correctly, then they will measure this thing correctly. And then later on, you can use that measurement. If the second bootloader is untrusted, then they can do whatever. They can measure fake data after you're screwed, right? So you have to verify the whole chain, and you have to make sure that this guy is trusted, the very first bootloader. And in the context of the TDX stuff, it's trusted because there is a key that's fused in it, and that's eventually signed by TDX, the Intel root keys. I don't know if TPM is super interesting, but I remember when I was looking at it, basically they were using these measurements. I think if the measurements didn't match what was previously seen, they would refuse to decrypt the hard drive of the user. So like you log in on your computer and you had disk encryption, and if it didn't match the measurements, then something was off, and so they were like, no, we're not going to decrypt the hard drive. But TDX has the same kind of idea. They have like these MSRs, I guess, model-specific registers, which are registers only for TDX platforms. And they use that to measure what is going to get loaded, what they're booting, which is obviously the firmware, the UEFI, /BIOS, the first thing you're booting. Apparently, they're not exactly the same thing, but I'm not going to get into that. Does that make sense, these measurements? I don't know if that was the greatest explanation, but basically, things are measured as you're booting things. You're like, trust me. If you trust me, this is what I'm going to start, and here's I'm measuring the hash, and you can use that measurement later. In TDX, that measurement is basically what's being signed in these attestations. So you're signing arbitrary data, right, according to your application logic, but you're also signing these measurements. And so on the user side, when you're verifying these remote attestation, you basically have to make sure the measurements make sense. And so usually you need to make sure that these measurements are reproducible, that they're deterministic, they always are the same. And you need to hard code them on the user side. And obviously, if you change your application, these measurements are going to change. Or if you change the image, these measurements are going to change. And so the user cannot verify them anymore.
So for the same software image from one T to another, would the measurements change at all or no? Is it both the uniqueness of the hardware and the software, or is it like one or the other? Or just the software, sorry?
So I think there's some stuff that's going to change. But if we only care about the TDs, right, and like this confidential VM, there's more acronyms. MRTD, which used to be called TDMR, but no, TDMR stands for something else, and runtime measurement registers, 0, 1, 2, 3. And so these are the ones that matter, and these are the ones that are going to be the same, depending on your computer and my computer, if we're running the same stuff. MRTD is basically the firmware. And these ones, they're runtime stuff that the firmware can measure, or like other stuff can measure. And I guess this is arbitrary depending on what you're doing. There's sort of a convention, I think, that comes from the TPM convention, but yeah. And so in the stuff I was looking at recently, basically the firmware will run some kernel, so in this case maybe the Linux kernel, and so they'll boot that, but this is provided by the host, so it could be anything. So you want to measure it to make sure that the user wants to see exactly the Linux kernel that they expected or something like that, and then the kernel will boot the first file system and then another file system, and all these things are basically anything that's dynamic and that can be changed outside of the firmware, you need to measure because you don't know what's happening. And usually the third one is used for the application. So the application itself can maybe maybe it's modular, it can take different things, and you will want to measure that. And so yeah, security-wise, this is where it gets tricky. You have to make sure that in your boot sequence, everything is like really deterministic. There's nothing dynamic that can be controlled by the hosts, and that's not measured. Or there's no bugs that, in one of the things that gets booted, there's no bug that allows you as an attacker to change what's going to get measured, or these kind of things. And this is where, like, I think I mentioned TDVF. So Intel has like their own projects that you can use, and I guess D-Stack builds on top of that. I don't know about these other guys and what they do. Yeah, does that make sense? Is there anything I can... So that means 40 minutes, right?
Actually, the measurement is not very... Yeah, it's not super easy to verify the measurement, especially on chain. For example, for RTMR0, it measures both the configuration and some and the kernel of your operating system. And the configuration is pretty hard because if you change the number of CPU or the size of the memory, it's going to change. And you don't care about how many CPU or how much memory usually when you're verifying the remote attestation. So the way to deal with that is you can try to reproduce the measurement based on any kinds of input. So you can imagine there's a function. You give the number of CPU, size of the memory, as well as the kernel, it gives you the measurement.
Yeah.
You can reproduce that. But in order to verify it on the blockchain, it's a little bit tricky.
Right, because the validator wouldn't be running the exact same specs.
You can enumerate everything.
Yeah.
You cannot put all the enumeration on the blockchain to verify.
Yeah.
Okay.
You could at least hash some of that, though, right?
Okay, say again?
You can at least compress that with some hashing, so
Theoretically, yes. Yeah, theoretically, yes. And in some cases, especially when you're measuring the PCIe devices like GPU, TPU, then basically the input is unlimited. You have so much combination, so you cannot really enumerate everything. But theoretically, you can give the input and calculate the right output. So like some kind of zkP or some other ways, you can reproduce that on the blockchain.
but then how you verify that was run correctly.
Yes.
All right, so I think we can stop here because I know we wanted to make a shorter video today, and we can we can discuss more, but this probably be a good end for the video. Cool. Well, hope all that made sense.